Hello everyone, welcome to lecture 4 of week 4 of the course Power Network Analysis, in which we'll continue our discussion on the fourth main module, which is transmission line parameter evaluation, in which we will discuss or understand how to evaluate inductance or basically flux linkage, magnetic flux linkage due to a current carrying conductor for points which are outside the current carrying conductor. So, whether we evaluate the inductance or the corresponding magnetic flux linkage, both would go hand in hand, as we would see in the slides to come. And this discussion will be built on the discussion which we had about evaluation of line inductance due to internal magnetic flux. Unlike electric field lines or flux lines which do not exist inside a conductor, magnetic flux lines, they can exist inside a conductor as well as outside a conductor, and hence the impact of these internal and external magnetic flux lines are different for internal inductance and external inductance. So, if you recollect, we considered a current carrying conductor as shown over here, which was carrying current I, and this current which is the conductor is carrying, we are assuming it to be it could be a AC current, could be a DC current. If it is a AC current, then at some point of time the current might be flowing outside the plane of the slide, and maybe for the next half cycle current might be flowing into the plane of the slide. For the consideration of the figure which has been drawn here, we are assuming that if it is a AC current, then we are focusing on one half cycle. The remaining other half cycle would also have a similar implication, and the current is flowing out of the plane of the slide if it is AC first half, or if it is a DC current, then the current direction doesn't change. And we understood that if we focus only on the magnetic flux lines, which are internal flux lines residing inside the conductor because of current I, then the corresponding internal inductance would have an expression of this form, which coincidentally turns out to be independent of the conductor size. It's also independent of the current I. Generally, electrical conductors are good electrical bodies and poor magnetic material, so we can also safely assume that the corresponding relative magnetic permeability is equal to 1. Mu naught is the absolute permeability, whose value is 4 pi into 10 to the power minus 7 Henry per meter. So, that is how we get this expression. And the direction of these magnetic flux lines, they are governed by the right hand rule. So, if we point our thumb into the direction of the flow of current, which is out of the plane of the slide, then the fingers are curling in the anti-clockwise direction, and that is how the red magnetic flux lines which are inside the conductor or blue magnetic flux lines outside the conductor, they are concentric anti-clockwise flux lines. They are closed loop lines as per the nature of magnetic flux lines. So, for our discussion today, we will take up the aspect of evaluation of inductance due to magnetic flux lines which are in blue color and are present outside the conductor. So, our assumptions remain the same, the idealistic assumptions that, in fact, all assumptions tend to be idealistic. So, we are considering those assumptions for the sake of easy analysis. What we are assuming is that the current density inside the conductor is always uniform. So, if current is I and the cross-sectional area for a circular conductor of radius r, then its corresponding current density would be nothing but I by the cross-sectional area of the conductor. For a conductor of radius r, that area is pi r square. So, ampere per meter, which is the current density. This number or current density is uniform at every point inside the conductor. That is what the meaning of uniform current density is. The return conductor for this current is far off, and that is the reason why the magnetic flux lines are all perfect concentric flux lines. That means they share a common center. Their radiuses may vary as per the distance of point of consideration. Distance increases or decreases from the center of conductor. And The conductor is perfectly straight, it is parallel, it doesn't have any straight bends, and hence these concentric flux lines, they don't sort of cross each other or overlap with each other. That's the essence of assuming straight conductors with parallel nature. The conductor radius is r, current is I out of the plane, as we have discussed in the previous slide. We focus on 2 points, P1 and P2. The distance of P1 is d1 from the center of the conductor, and point P2 is at a distance d2 from the center of the conductor. D1 and D2 here, both of them, they are going to be greater than R. They can at best be equal to R on the surface, but they should not be less than R, because we are focusing on inductance evaluation due to external magnetic flux lines. We are not focusing on internal magnetic flux lines. The impact of internal magnetic flux lines has already been considered in the previous lecture. So, by right hand rule, as I have already explained, by right hand rule, if the thumb points in the direction of the flow of current, which is out of the plane of the slide, the fingers would curl in the anticlockwise direction, and that's how the directions of flux lines are dictated or decided. We are considering a similar cross section the way we discussed in internal inductance evaluation. We are considering a cross section of width dx, which is at a distance x, which is more than r, which is basically indicating that x distance is referring to a point which is outside the conductor, and at a distance x from the center of the conductor, we have taken a cross section dx, and the length of this cross section is dl, which is again being measured along the periphery of this circle, whose radius is x from the center of the conductor. So, the way we understood that why the length vector, magnetic flux intensity, magnetic field density, flux density, why they should align along the tangent of the point along which this distance dl or dx is being measured. The answer is simple. As I mentioned, since we are measuring the distance dl along the circumference of this circle whose radius is x, the corresponding dl vector would definitely lie along the tangent. So, basically this is the circle, if this is the circle, then this line is nothing but the tangent along this circle, which is having a slope of 90 degrees with respect to the radius being drawn from the center. So, this angle is 90 degrees, and along dl vector, magnetic flux intensity or field intensity would also lie, because we are looking at the impact of the flux lines from the current consideration perspective, and it is by nature of these magnetic flux or field intensity that the Hx vector is also parallel to the corresponding dl vector. And magnetic field density for a medium where the medium has having constant permeability is not changing with time, then the magnetic flux density is nothing but permeability into the magnetic field intensity, where this permeability is mu naught into mu naught being the absolute permeability, and mu r is the relative permeability of the medium in which these flux lines, magnetic flux lines exist. So, if Hx is along dl vector, then it is imperative that mu being a scalar quantity and is constant, it is not changing with time, Bx would also be parallel to the dl vector, and that is the reason how the corresponding vectors are marked. So, if we now focus on the cross section that we have considered, and if we were to continue measuring or continue shifting these dl along the circumference of the circle of radius x, then eventually we would get a hollow cylindrical tube whose internal radius would be x, the width would be dx, and the length of this cylindrical hollow tube would be equal to the length of the conductor which we are considering. So, that is how we focus on this. If I were to complete this entire cross section, pardon me for the inconsistency in not being able to draw a perfect circle, then this entire tube which is going to be our point of concern for finding out the impact of external magnetic flux lines, this would be a cylindrical hollow tube whose attributes or parameters are what are given over here. The radius is x and the distance or the width is dx. Also, I would like to briefly point out one thing. We'll also be discussing this aspect in detail when we go to the upcoming slides, that our magnetic flux lines the way they are as of now, these magnetic flux lines, they are not along the length of the conductor which is carrying current. These magnetic flux lines, they are tangent to the surface of the point or the circumference where we are considering this point. So basically, if I were to focus on magnetic flux lines at the periphery of this conductor, then the corresponding magnetic flux lines, their corresponding strength is along the tangent. Reason being, magnetic flux lines, they are always closed loop lines, they are concentric lines, they are parallel to the surface of the conductor which is carrying the current I. So that's the reason, also another reason why h of x is along the tangent, and if h of x is along the tangent, permeability remaining constant, b of x would also be along the tangent. So if we have to understand that this magnetic field density or flux density, it is not along the length of the conductor. So let's say if I were to draw the corresponding cross-sectional or frontal section of this conductor, which if I were to mark it over here, then the current is, as per this direction, current is flowing along this length I or along the length I, and the magnetic flux lines or field lines, they are not along this current. They are actually aligned like this. If this is the front section, if I were to draw for this corresponding, sorry, not the front section, this is actually the front section which is what is shown over here. This would actually serve as the side section of the cylindrical portion that I am looking at. So if I look at it from the side, then this is the entire length along which current is flowing, and the field lines or the flux lines, they appear to be perpendicular to the direction of current. So if I have to find the impact of the magnetic flux lines in terms of flux linkages, I should be very careful in figuring out the cross section through which these flux lines are flowing. So please keep that aspect in mind. We'll again come back to the same aspect in a short while. So our Ampere's law would be very useful in figuring out the corresponding value, in sort of evaluating the corresponding values of flux intensity or the flux density. Ampere's law simply says that the line integral of dot product of magnetic field intensity and the distance vector or length vector dl is nothing but equal to the net current which is present inside the line integral which is carrying this surface. So basically the net magnetomotive force MMF around a closed path as per Ampere's law is equal to the net current enclosed within this line integral path, which is also equal to the dot product of the magnetic field intensity and the corresponding dl vector. And similar to the discussion that we had in the previous slide or the previous lecture, where we are considering a straight conductor, parallel conductor whose current density is uniform. So if we try to find the value of h of x at a distance x from the center, where this distance x could refer to n number of points along this circumference, then at any of these points the value of h of x is going to remain the same. Reason, the current density is same, I by pi r square is same throughout these points along the conductor is straight and parallel. So h of x, no matter the value of x distances, I mean not the value of x, but no matter what point I take along this circumference or circle which is at a distance x from the center, the value of h of x is going to remain uniform. Also, hx and dl are parallel vectors. So if you recollect our previous discussion where dot product of two vectors is nothing but equal to the corresponding magnitudes with cosine of the angle between these vectors. For parallel vectors, the angle is going to be 0 degrees. So this dot product, which eventually results into a scalar quantity, would be nothing but h of x into dl. So in order to sort of simplify that, if I have to find this line integral, I can make use of two properties. One, the dot product is a simple scalar term, and h of x is going to be same along any point I take on the circle of radius x. So essentially this integral can be simply stated as h of x integral of dl, which should be equal to I. since our point of concern is outside the conductor, so the net current present is I itself, which is the total current present inside the conductor. For internal magnetic flux lines consideration, this I was replaced by I of x, where I of x was portion of current depending on the distance from the center x along which the circle consideration was made. So, x was also a function of I of x, whereas over here in the expression I, it's independent of x. So, given that the current density is uniform, H of x is going to be uniform at all points in the circumference of circle x. So, we can make use of that property along with the property of dot product of two collinear vectors, and we get this beautiful expression for H of x, where integral of dl is nothing but the circumference of the circle whose radius is x. The circumference is going to be 2 pi x. So, we have H of x as I by 2 pi x. Now, once we know the magnetic field intensity or flux intensity, we can also find the corresponding magnetic flux density B of x, where we multiply mu with H of x. The medium outside the conductor is likely to be air, and that's the reason why mu is replaced by mu naught, which is absolute permeability, equal to 4 pi into 10 to the power minus 7 Henry per meter. And the relative permeability of air is also considered, where air is a very bad conductor, not only from electrical perspective but also from magnetic perspective. So, mu r of air is equal to 1. It's as good as the conductor is being considered in a vacuum space outside the conductor. So, B of x value we can also find from the expression of H of x. Once we know the field intensity and the field density, then we can evaluate the corresponding stored magnetic energy density in exactly similar lines the way we evaluated for internal magnetic flux lines consideration. So, field energy density, magnetic energy density is half of B of x into H of x. We substitute those values of B of x and H of x, we get this expression. And now, we will again go back to the cross section or side section that we were talking about. This is the front section of the corresponding conductor which we are looking at. If we look at the side section, which is along the length of the conductor, then for the side section it appears that the current is flowing like this, whereas the field lines or flux lines, they being concentric and parallel to each other. The field lines or flux lines B or H, they are perpendicular to the side section which we are looking at. And now, if this field lines are flowing along the periphery or circumference of the point of concern where we are looking at, so and it is not along the length of the conductor. So, if we have to find the energy density, which is UBX multiplied by the volume in which this magnetic energy density is present, then it would nothing be equal to the circumference along which the dl vector is being measured, which is essentially the volume of the cylindrical hollow tube which we looked at. This tube is same as the length of the conductor. Since we are evaluating our parameters on per unit length basis of the conductor, so we can easily consider the length to be equal to 1, where 1 could be 1 meter, 1 kilometer, 1 mile, and accordingly this per meter unit could also change accordingly. And 2 pi x into dx is nothing but the front cross section of this cylindrical hollow tube, which we are multiplying with unit length 1, which gives us the volume of this entire cylindrical hollow tube. So, we can find the unit energy which is being stored in this hollow tube. So, stored magnetic energy density multiplied by the corresponding volume of the cylindrical hollow tube gives us this expression of unit energy which is stored. Now, if we want to find the entire energy, then this entire energy E would be nothing but integral of d of E, which when substituted with this expression over here gives us our value of total E is equal to mu naught I square by 4 pi natural log of d2 by d1. We are considering or trying to find the stored magnetic energy between points P1 and P2, which are at distances d1 and d2 from center of the conductor. So, the corresponding energy which is stored in between this section for the current carrying conductor, which is the value of E which we have evaluated, is nothing but mu naught I square by 4 pi natural log of d2 by d1. This energy is also equal to half Li square, where I is the net current present in the conductor. And from here, if we correlate or try to find the expression of L, which is going to be the inductance between points P1 and P2 outside the conductor at distance D1 and D2, which are more than R, then we have this natural log expression as the entire external inductance between points P1 and P2 outside the conductor. We can, so in a way, we have got to know that this is going to be our external inductance due to external magnetic flux lines. We also know that the internal inductance, which is LINT if I were to represent, is nothing but mu naught mu r by 8 pi. That's the only expression that we get. It is independent of the radius and independent of the current I. So basically, L internal is the entire inductance of this conductor which is carrying current I of radius r, and L internal is the internal inductance between center of conductor and the radius at the surface. That is what L internal means. So if we have to find the net inductance of a point P which is at a distance d from the center of conductor, we have two inductances in series. The one inductance which is inside the conductor is L internal. The other inductance is the inductance outside the conductor, which is L external. And if I were to sort of mark a point C here, then it is L external C comma P, where C is at a distance r and P is at a distance d. So if I now combine these two inductances to find the overall inductance at a point P from a distance d from the center of the conductor, then I can easily get net L to be equal to LINT plus L external C comma P. Please keep this thing in mind, because why are we adding these inductances? Because from the center it appears that they are series combinations, and that's how we can easily add these two inductances. We'll again come back to this expression in the next few slides. There is also an alternate way of finding this inductance between outside points of a conductor due to external magnetic flux lines. So we have seen in our course of discussion that the magnetic flux density is nothing but mu naught I by 2 pi x, where x is at a distance x from the center of conductor and it is outside the conductor. So x is essentially more than r here. So if we know the corresponding magnetic flux density, and we again recollect our side section where current is along I, the flux lines are perpendicular to the side section. Since the flux lines whose strength is or density is B, they are along the periphery or outside the conductor. So essentially B of x is not flowing inside the conductor or outside of the conductor in terms of the slide of the plane. The magnetic flux lines, they are actually along this section whose width is dx. So if I have to find the corresponding flux linkage or unit flux linkage, which I denote by d of L, remember flux linkage, we have seen the lambda or the variable to be lambda. So if I find the unit flux linkage, that flux linkage will be nothing but the flux density multiplied by the area through which these flux density or flux lines are passing through. Now the area which I have to focus on is not the cross-sectional area of the conductor, it's not the surface area of the conductor, it's essentially the area along which this width of section dx and dl is considered. So if the cylindrical hollow tube is of width dx and the area is not with respect to the periphery or circumference of the circle of radius x, but it is actually width dx multiplied by the length. We are using unit length 1, so this side section is of unit length 1, then the area of this cross section along which magnetic flux density is existing is 1 dot dx. So from here we can find d lambda, which is mu naught I dx by 2 pi x Weber turn per meter. Now we can also integrate this lambda. So net flux linkage between points P1 and P2 would be integral of d of L, which we do turns out to be this expression again. And we also have seen or recollected that inductance value L for a medium where permeability remains constant is also equal to lambda by I, where lambda could represent the phasor quantity and I could also represent the phasor quantity. We are considering I and lambda to be the phasors here. They could be AC current, they could be DC current. So L by lambda or lambda by I is also a measure of L. So from here we can also find lambda by I. So lambda by I would essentially be mu naught 2 pi ln of d2 by d1 Weber turn per meter, which is also the same expression which we got from the magnetic stored energy expression perspective. And now with this, if we try to find the net inductance at a point which is at a distance d from the center of the conductor, and this d is outside the conductor, then we have two inductances. One is the internal inductance between center and the surface of the conductor, which is of radius r, which is coincidentally independent of r, and the external inductance is between point on the surface of the conductor and the point which is at a distance d from the center of conductor. So as per this expression, this is the corresponding external inductance. Now if we combine these two, we can easily get the overall expression LD to be of this form. Now how do I get this? It involves little bit of a mathematical reorientation. So mu naught into mu r by 8 pi can also be rewritten as mu naught by 2 pi into mu r by 4, which is also equal to mu naught by 2 pi natural log of e to the power mu r by 4 divided by 1. This could also be rewritten as mu naught by 2 pi natural log of 1 by e to the power minus mu r by 4. Now if I try to add this term with the term sitting over here, then essentially I would get d as the same d which is present over here. D into 1 is d, and r into e to the power minus mu r by 4 is this particular term. So that's how the corresponding net inductance expression can be evaluated. Now there is a very specificity about the expression that we have obtained here. What we see here is generally for conductors the value of mu r is close to 1. So essentially mu r by 4 would always be a positive quantity, which means e to the power minus mu r by 4 would also be a positive quantity, and this positive quantity is getting multiplied by the corresponding, it would be more than 0, but it would definitely be less than 1 because mu r by 4 is positive. So, e to the power minus mu r by 4 be a value less than 1. So, we are trying to multiply a quantum or number which is positive and less than 1 with the effective r. So, this term actually is less than r for practical conductors, and this gives a clue or an indication that because of external flux lines or magnetic flux lines, the overall effective radius of the current carrying conductor reduces, which is also responsible for skin effect. The overall cross section of conductor is reducing, the current density is getting affected, more current tries to flow on the periphery, and the reason being that the overall cross sectional area is getting compressed because of inductance in the conductor, and that's how we can also understand why AC resistance is more than the actual DC resistance of conductors. That would be all for today's discussion. We will take up the discussion of evaluating magnetic flux linkage or flux lines values of a conductor in a group of conductors in the next discussion. Thank you.